Good. Started already. Okay, fine. Good. Okay, so we were talking about the analytic functions and which will follow by the discussion on harmonic functions and constructions on analytic function. So whatever I'm writing here over the pen, it's visible, right?
Yes, yes, sir.
Okay, okay, okay. Because I observed something strange over the weekend. I was just talking to someone, and then whatever I was writing, it was not visible. Then I realized whether this is happening in my lecture also. So it's visible, yeah. Usually, whenever whatever I write there, it's visible to you, right? Okay.
Yes, sir.
Oh, very good then. Perfect. So let's just quickly review. So we were talking about the CR equations, right? So CR equations were the necessary conditions for differentiability at a point. So if these equations are not satisfied, then what we know that fz cannot be differentiable. So f prime z will not exist. But if the CR equations hold, in that case f may or may not be differentiable, because this is just the necessary condition for differentiability. Well, so then we had these examples. I think this was a trivial example where we have seen that CR equations do not hold at any point, so we cannot talk about differentiability or analyticity, right? So there was a function fz is equal to z real z, and yeah, uxy is equal to x square and vxy is equal to xy. So we have ux 2x and uy as 0. And again, in terms of v, we have these derivatives. The CR equations hold do not hold at any point except z equal to 0. So here something interesting, that the CR equations hold only at z equal to 0, nowhere else. So when we got that CR equations hold only at a point, then definitely we can say that this function is not differentiable. This function is not differentiable certainly at any other point than z equal to 0. Z equal to 0, we don't know about the differentiability in fact, but what we know that except z equal to 0, the function is nowhere differentiable, right? About z equal to 0, we don't know. It may be differentiable, but it may not be differentiable. This is what the information we have with at this point of time. So what we can conclude, since the function is not differentiable except z equal to 0, if at all it is differentiable or does not differentiable at z equal to 0, we don't know. But we know that it is not differentiable anywhere else. So definitely the function cannot be analytic, because for analyticity you need differentiability not only at that point but also in the neighborhood of that point. Well, so nowhere analytic, that is for sure we can say, and it may have a derivative at 0. So that
Excuse me, sir.
yeah.
So actually, analyticity is not defined for a particular point, sir. Means if the domain is only a particular point, then can we not say that it is analytic at that point?
Yeah, we, as I said, as I also stated the definition of analyticity is very, slightly different, because there you are talking about it is defined at a point also, that you say that the function is analytic at this point if it is differentiable at that point and also differentiable in the neighborhood of that point. Did you get my point?
Okay. Okay, so yes,
So
sir. Got it.
differentiability at a point or analyticity at a point is fine. It makes sense, which says that the function is said to be analytic at a point if it is differentiable at that point, and not only just differentiable, it is differentiable in the neighborhood of that point also. So the point is, it is more of theoretical nature, because once you are talking about analyticity at a point, only at a point, then you have already that the function is differentiable at that point, and also function is differentiable around that point. So then you move from that point to slightly, you know, the in the neighborhood where the function is differentiable, and indeed you have there also the same condition, so the function will be analytic there also. So you will not see, you will not realize any example, or I haven't seen that you will say that function is analytic only at this point, but nowhere else. Differentiability is fine. You can say that the function is differentiable only at this point, but nowhere else, like we will see in some of the examples, but not for the analyticity, because analyticity anyway, the definition at a point itself says that there will be a neighborhood where the function will be differentiable. Correct? So,
Yes,
for
sir, got
instance,
it, sir.
here,
So, sir, in this,
got it? Yeah.
so, sir, in this,
Your voice was not.
one point. So,
Hmm? Your voice was not clear. Hmm? Okay, so the function is differentiable only at z equal to 0. Function is differentiable only at z equal to 0. We can make such a statement, but I don't see any example where you can say that it is analytic only at this point, because that cannot happen, because analyticity itself is that differentiability at that point and also in the neighborhood. So you have a region always where the function will be different, analytic in that case. Okay, let's go through some other examples, then probably it will be clear. So here again, a similar nature, that the CR equations are satisfied only at z equal to 0. So f is not differentiable at any z other than this 0, that we can guarantee. It may have derivative, it may not have derivative at z equal to 0. That is another point. And when we check, we realize that again that function is differentiable at z equal to 0, but it is nowhere analytic. It is nowhere analytic. So that example is also clear, I suppose. And then we had this example where fz was a square root of xy, and let's go through quickly because we have already seen this. So again, the CR equations are satisfied at the origin, So and we will check now the differentiability. So if you see that differentiability here, f prime z does not exist. So in this example, you have seen that f prime fz is not differentiable at origin, although the CR equations are satisfied. Yeah. So the CR equations are just the necessary conditions, right? Not something sufficient. They are just necessary for differentiability. Yeah? They are necessary for differentiability at that point, or analyticity, of course. So you have sorry. So something happened. Okay. Just the last example maybe. So we have the CR equations. We want to show that they are satisfied for this function, for example, sine z, right? Sine z. So for CR equations, we need that u and v, right? So we need to separate that sine z into that real part and that's that imaginary part. So sine z, you can write down as x plus iy. So this z here is replaced by this x plus iy. And then you have this sin x plus sin x cos y and plus cos x sin iy, that sin a plus b formula you can apply. And then this cos y formula, yeah, you have this cos x formula, right? Do you remember this cos x, which is e power x, ix e power minus ix over 2.
Yes, sir.
Correct? So
Yes, sir.
this
Yes.
I have exactly used this one here, but it was iy instead of x, there was iy. So therefore this is square terms are coming. And similarly here also. And I square minus 1, you know, And then I'm using that another formula for hyperbolic. Do you know also for hyperbolic?
Yes.
So e power y
Yes, sir.
minus plus e power minus y by 2, that is the cos hyperbolic y, and with the minus sign it is sine hyperbolic y. So we have cos hyperbolic and then we have sine hyperbolic terms there. So this is your u and this is your v term. So uxy is sin x cos hyperbolic y and vxy is cos x sin hyperbolic y. And then naturally you can go for the CR equations and you will see ux. So if you just differentiate with respect to x, you will get this cos x cos hyperbolic y, and v when you differentiate with respect to y, so cos sine will become cos, and you have again the same derivative. Similarly, for uy is equal to minus vx, that also follows. So the CR equations are satisfied everywhere, and naturally this sign z then is because those continuity of the partial derivative is also required, right, to declare that the function is analytic. So the continuity of these ux, uy, and so on, this is trivial. So for these functions, so nice functions. So here the CR equations exist, and also those partial derivatives are continuous. So the function sin z is also analytic. So there is no problem to say that this is analytic everywhere. Okay. Now we will switch to this another topic, which is harmonic functions. Yeah, harmonic functions. So you don't have to go much into the detail. So just a definition which I will give you that what are these harmonic functions. So a function uxy which satisfies the Laplace equation. What is that Laplace equation? This is called Laplace equation. Uxx, the second derivative of u with respect to x plus second derivative of u with respect to y equal to 0. That is the so-called Laplace equation. And if a function satisfies Laplace equation in a domain D, then this such a function is called harmonic in D. It's a harmonic function in D. So what is the relation of the, because this is not a topic here to go through what are harmonic functions and so on, why it is being taught here, what is the relation to, because there is some relation with this analytic function which we are talking about here now. So suppose this, if fz uxy plus I vxy is analytic in a domain D, if it is analytic in a domain D, the point here is then u and v satisfies this Laplace equation. Yeah, that is the only connection. So if this fz is analytic in a domain D, then u and v, these components u and v, your components of your function fz, u and v, they satisfies Laplace equation. So that means the uxx plus uyy will be 0 and vxx plus vyy will be also 0. So that is the only connection with the analyticity which we have, that if a function is analytic, then it's real, and this complex, the imaginary part, they satisfy Laplace equation,
So,
that is uxx uyy and vxx vy equal to 0. Yeah.
so that means that a function, whenever it is harmonic, it will also be sorry, whenever it is analytic, it will also be harmonic.
These parts u and v, this is what we said. If this fz is analytic, then u and v satisfy Laplace equation. That means u and v are harmonic functions.
So u and v only will be harmonic, and
I had one
analytic
question.
will be the whole function.
U and v, yeah.
I had
So
one
if
question.
fz is analytic, then this u and v are harmonic. That's all.
Sir,
Hmm.
sir, you gave a proof right last day or today also when you were revising that root x root what?
Huh? Yeah, square root that xy. You are not audible.
You're muted, I think.
Yeah.
So I was muted, anyways. But there was this one example, right, where the equation followed CR equation but was non-differentiable, right?
Yes.
Sir, so like if the equation or a function satisfied CR equations, that means it is analytic, and again it is since it is analytic, it will also satisfy Laplace equation we are considering, right?
But who said that this CR equation it will be analytic? That example we have seen now that the function satisfies CR equation, but it is not analytic. We have several examples.
Sir, does analytic doesn't like confirm differentiability?
What do we see here? That the CR equations are satisfied?
Yes.
True? But the function is not analytic. Function
Sir,
is not differentiable in
not
fact.
differentiable. Differentiable and analytic is the same.
Are Baba, differentiability comes first. If the function is not differentiable, we cannot talk about analyticity. Analyticity is more than differentiability, right? If a
Oh.
function is not differentiable at a point, then for sure it is not differentiable. What is analyticity? What is analytic functions? They are differentiable.
Yes.
So if I say at one point the function is analytic, that means it is differentiable at that point, and not only at that point but also in the neighborhood. So it is more than differentiability, right? The
Yes.
analyticity is more than differentiability.
Got it, sir. Okay.
Yeah. So this is all these examples we have shown that CR equations will not ensure you even differentiability. Forget about analyticity, right? Here also CR equations were satisfied, and here were satisfied at z equal to 0, but the function is not differentiable at z. Okay, in this particular example it was differentiable also, but in the earlier examples again the function was not differentiable. So CR equations.
So that means the CR
satisfied.
equations are necessary conditions, but not sufficient
Yes,
conditions.
this is what from the beginning we are.
So the sufficient was that they have to be continuous also. Like
Yes.
in the,
These derivatives
Yes.
must be continuous also. True.
So
Otherwise,
Laplace equations will be like these harmonic function will be like a necessary and sufficient condition, right?
at what we said, if fz is analytic, it's one way again. See, what is the statement? The statement is, just wait. The statement is, if fz is analytic, then u and v will satisfy Laplace equation, correct? If fz is analytic, then u and v are harmonic. This is the statement.
Oh, like reverse is not true always.
Yeah, we are not talking about reverse at this moment. We will come to that point also. Okay.
Okay.
At this stage, we are talking about if fz is analytic, then u and v satisfy Laplace equation. Fine. Just actually, again, I have written a sketch of the proof because it's not a complete proof. Let me just tell you, because for some reasons which you will see, the complete proof is really lengthy proof. So the proof will go as, so we assume that fz is analytic, right? Fz is analytic, we assumed. So now we will show that del 2u over del x square plus del 2u over del y square will be 0, right? So del this is the meaning is del over del x of del u over del x, del over del y of del u over del y. And then you have this CR equation. So fz is analytic, must hold, of course, right? So we can apply here CR equations. Del u over del x, del u over del y. Just write down in terms of v. So we have del u over del x is equal to del v over del x, or del v over del y, and del u over del y is del v over del x. True?
yes, sir.
Yes,
So
sir.
CR equations we can apply. And now, so this is nothing but del 2u, del 2v over del x del y, del 2v over del x. Here I have used that continuity assumption of v. So that means the mixed order partial derivatives are equal. And here is what I meant by that. This is a sketch of the proof, because you don't need any other assumption. The result is that this result is okay. This result is fine. This result is fine. You don't need any other condition there. Fz is analytic, u and v satisfy Laplace equation. That result is fine. But I have used here just to show, I mean, this is a sketch of the proof, so that this del 2v over del y del x is equal to, I use that del 2v over del x del y, the continuity of these partial order derivatives I have assumed here, which can be proved again. So there is a lengthy proof, which, as I said, this result is fine, which we have stated there. Fz is analytic, u and v will satisfy Laplace equation. You don't have to worry about that. But the formal proof we are not giving here. Yeah.
Sir, why should we assume it is already true if it is analytic?
It is not.
Sir, it should be continuous because it is analytic.
Why it should be continuous? Can you prove?
Its partial derivative should be continuous because analytics tells that differentiability exists at neighborhood point also.
Differentiability exists in the neighborhood part also. Yeah, that point is correct. So at a point, then in the neighborhood, the function is differentiable. That is fine.
Yes, sir. If differentiability exists at neighborhood point, that means partial derivative should be continuous. Then differentiability will exist.
Now, how do we know partial derivative should be continuous? That part is missing still.
Sir, for if any function is differentiable, then that means it should be continuous.
No, not function continuous. We are not talking about the continuity of the function. We are talking about the continuity of the derivatives. We are talking about here the continuity of the derivatives, not the continuity of u and v. They are continuous, that's fine.
That means partial derivative may or may not be continuous at that point.
Yes, I mean, at this with this knowledge, whatever we have, we can't claim anything about those. Huh?
Sir, excuse me. If function is differentiable, then it will be differentiable along all path. The limit will exist along all path, right?
Yes.
Then we will go along the path along which we are taking the partial derivative.
Yes.
So it has to be continuous now, right?
No. Again, continuity kahan se aa gayi? Existence is fine.
Differentiability implies continuity, sir.
Differentiability implies continuity of u. If u is differentiable, u is continuous. Differentiability implies continuity, that is fine. So if u is differentiable, I would say u is continuous. That is okay. Yeah, so it's not that much straight, because see, you have seen that continuity of partial derivatives plus CR equations. That is sufficient condition. We are calling that sufficient condition, right? So yes. Here we have taken the assumption that Fz is analytic only. So analyticity does not imply the continuity of those partial derivatives directly. Did you got my point that this coming from here to here, it is not just obvious?
Yes, sir.
Yeah, so it's a sketch again, it's a sketch of the proof. So here you have this and then these are equal, so you get 0, right? Similarly, for the V also you can use the CR equations and then you can show that this is also 0. So once the function is analytic, the U and V, they both will satisfy Laplace equation. So if U is analytic in a domain D, analytic harmonic, sorry, the harmonic we're talking about. U is harmonic, that's another theorem. if u is harmonic, so you have a function u which is harmonic in a domain D, then for some v, we have to see what v, u plus iv defines an analytic function for z in D, and we will explore this portion now. So the meaning is, if I give you a function u which is harmonic, then you can actually find the corresponding v so that this becomes analytic. This becomes analytic. You get this result?
Yes.
Yeah. So if
Yes,
one of
sir.
them is given, either u or v is given, which is harmonic, of course, they have to be harmonic. Then I can find the other one so that the function u plus iv will become analytic. Yeah. What was your question?
So there will be a unique V for every U.
Yes, kind of unique, but there will be some addition. I mean, constant term might be extra, so that we will come to that point. Yeah, unique to a constant, so the constant can vary still, that function by a constant.
So since
The
we have
function
this,
u and v. Oh, sorry.
yes, sir. I was saying that since we have those CR equations, we can find V from there if we have U as a harmonic
Yes,
function.
yes, exactly. So the function u and v are called harmonic conjugates, another term, right? U and v are called usually harmonic conjugate, where u plus iv defines an analytic function. U and v are called these harmonic conjugate to each others. Anyway, now we'll come to the construction of this analytic function once u or v is given. So suppose this u is given as e power minus x, x sin y, y cos y is harmonic. Find v such that u plus iv is analytic. So just try to understand those steps, because whatever function is given, you will follow the same steps. So there's nothing much theory behind this, only the CR equations, as one of you has mentioned now. So you have the ux, compute ux. That is the first step. So u is given, you can get ux, right? You can get ux. So you have this ux in hand. Well, uxx is this one, uy and uyy is this one. Just to check that this is harmonic, yeah, that's just nothing else. So which will show that the u is harmonic, because those things will cancel out, whatever you have there and here, they will cancel out each other. So you have uxx plus uyy equal to 0. So u is harmonic. That part is just the calculations, nothing else. So we have this del u over del x, we have del u over del y, correct? So pick this del u over del x, pick this one. What to get out of this now? Can someone tell?
Vy. So Vy.
Vy. Well, so what I will go, I will use this CR equations. That means del v over del y is equal to del u over del x, correct?
Yes, sir.
Which is given here already, as you mentioned. This is given, right? So
Yes, sir.
now del v over del x is minus del u over del y. So this is given here. We have this information. Finally, we need v, right? So now this first equation, get v, we will partially integrate with respect to y, right? We'll integrate it with respect to y, the first equation, del v over del y is equal to this one. We will integrate with respect to y. So when you integrate here with respect to y, the sin y will become cos y with minus sign. So minus minus will be plus. Then you have e power minus x and then y cos y. So this integration, product rule. Again here sin y will become cos y with minus sign. And plus, what is this plus?
It's a constant
It's
should
a
have been, but
constant, right? Because you were talking about the partial integration with respect to y. So here anything function of x can come, right? It's an arbitrary function of x. So we got v here. And just further simplification, we have the information del v over del x. So from here also we can get del v over del x. So v is this one for the just a slightly more simplified version. So we have this v. So let's go to v is this one, del v over del x is this one. So out of this v you get del v over del x. Del v over del x, just integrate once. You have f prime x. Do you are you following this?
yes, sir.
Okay.
Yes.
And then you set, I think we have done similar thing somewhere in two variable calculus, if I remember. So del v over del
Yes,
x.
sir.
Yes, exactly. So del v over del x is this one, which is equal to this minus e power x, x cos y.
In exact
Exact
differential
differential
equation.
equation. Exactly,
Yes.
exact differential equation we have done. Now here you can cancel out. So x cos y is getting cancelled, y sin y is getting cancelled, cos y is getting cancelled. Then you have f prime x equal to 0, and which implies fx is constant, and this constant can be added to that function. So we got this v, that v is equal to this one with a constant, and therefore that u plus iv with this v will become analytic function. Yeah. So this evaluation of the other one, once the u is given or v is given, whatever, you can compute easily. Just apply CR equations, integrate that partially, and then differentiate and equate to the other one, and there you will get this kind of this arbitrary function, and then put it again back to this, and you are done. So all the steps are clear?
Yes, sir.
Okay, very good. So can you just try with this? Find an analytic function ux plus ivxy, given that uxy is equal to x cube minus 3x square. Just can you do it in a minute?
So can you just go over the steps once again briefly? Like I lost in the middle.
Where? Which one?
So can you just like from the first, just in 1 minute, can you just go over it once?
See, yeah. So it's simple. So you have del u over del x, you have del u over del y, because u is given. You can compute del u over del x, del u over del y. Then
Yes.
you get to CR equation. This del v over del y is given to you, del v over del x is also given to you. Correct?
Yes, sir.
Then you integrate this to get v, right? You want to get v. So you integrate with respect to y. The only thing now here, integration of constant will be function of x, because you are integrating with respect to y. So you can have a function of x, any arbitrary function of x there. Well, then you simplify. So you got this v here, and del v over del x was given another equation. So here this v can be again differentiated to get del v over del x, and there you have del v over del x. Equate them and you get f prime x. So f prime x in this particular case is coming to be 0. So that means fx is just a constant, and then v is there. Then you can just put that fx as constant there. So you have v.
Okay, sir, got it. Yes.
Sir,
Yeah.
we can convert it into exact differential equation and then solve it using previous method also.
Why you want to convert to exact differential equation and all?
Sir, there we have more flexibility, sir, more rules to solve them. This may be quite lengthy actually.
What is lengthy? V is given. See, this is not lengthy. I have just done few lines here. So see, This equation is directly given to you, right? U is given differentiate with respect to x. Then you have del v over del y, just integrate in line and then put it the other one. Whatever way you do, you have to do. I mean, I don't think you will get any benefit of going to exact differential equations and all. Yeah, you can try yourself, whatever. You know?
So we can do it the other way also, like uy we are getting, so we convert it into minus
Yeah,
vx and then take the partial
yeah,
integration there.
yes. That also you can do. Huh?
Yes, sir.
Ultimately, using both the equations, you have to find out what is v. Yeah? Do it here. U is given. That's simple, right?
So is it
Sir,
3x
3x
square
square
y
y minus
minus
y
y
cube
cube?
plus c.
Got it already?
Yes, sir.
Okay,
Yes,
CR
sir.
equations, then
Minus.
v, then you have prime x, cxy, again this is 0, a constant, and then you got v as 3x square y minus y cube plus constant term. True? Plus a constant term. And then we have fz as uxy plus ivxy. Here maybe it's possible here to again merge, get back to z form, so it is actually z cube plus k, right? Fz is z cube plus k. Fine.
Sir, K is complex constant, no?
Yes,
Iota C.
yes, it's any arbitrary constant, so in complex plane.
Okay, sir.
It can be a real number, it can be purely imaginary, it can be anything. That will not impact or not disturb this analyticity or the function v.
Okay,
CR
sir.
equations are necessary, not sufficient. That's what we have learned through many examples. Fz is analytic, then u and v satisfy Laplace equation. And we know now that given u how to find v or vice versa. Clear up to this point?
Yes,
Yes,
sir.
sir. Okay.
Yes, sir.
So what I will do now, I will switch quickly because we have at least 15 minutes to the integration part. Though we will start integration again tomorrow, there is no problem. But at least some idea we will get on the integration, the line integral.
Sir, I have a doubt.
Yeah, please go ahead.
Sir, if a function is analytic, then
Yeah.
is it necessary that del u by del x, del u by del y, and all those, or del u by del x and del u by del y will be continuous?
Actually, yes, that is true. There.
Means if it is sufficient, so the converse will also be true, right? Ux, uy, vx, vy all will be continuous if function is analytic.
No, converse is always true. Why you are saying this? So that
Because it
result
is a
says.
sufficient condition.
The sufficient means you have more condition, right? You don't need those conditions, but you have little more. So you have CR equations, you have the continuity of ux, uy, vy, that will imply analyticity. That is fine, right? So, but it does not mean that analyticity will imply that. The sufficient condition doesn't say this, isn't it? Are you getting my
Means
point?
if a function is analytic, then it may so happen that ux, uy